Hey everybody, it's Mr. N here, and we are going to talk about the definite integral today. Alright, so if you take a look back at 5-1, we can make those rectangles on a continuous curve from A to B with left endpoints, right endpoints. I haven't covered midpoints, I'll do that today. And we have other techniques as well. And we can find the area of each of those rectangles and then be able to determine what the area under the curve is. This whole process, by making these rectangles, is known as Riemann sums. Some pronounce it as Riemann, but I'll go ahead and say Riemann. So these are Riemann sums. Now, it's named after George Friedrich Bernard Riemann, and he would look at the dates. This always gets me. Look at these dates: 1826 to 1866. Right? 40 years right there. Just imagine if he lived longer, how much more we would have from him. But if you want to take a look at the history of Riemann, here's a good website to do that. And here's another one to give you an idea of how to visualize Riemann sums. So I'm going to start this lesson by doing a Riemann sum example, which is what we did in the last lesson, but we didn't call it that. Now we know the official name for it. It's called a Riemann sum. So let's take a look at this first example. It says, find the area under y equals x squared from 0 to 2 using left endpoints and using 10 rectangles. So first we need to determine what our delta x is, our widths, right? So delta x is going to be our width. Let me get the right color here. So we have widths, and these are delta x, and this is going to be b minus a over n, and that's what we learned in the previous section, b minus a over n. So over here, from 0 to 2, there's my a and b, and this is a closed interval, so I'm going to say 2 minus 0, and then n is the number of rectangles I'm going to make. I'm going to make 10, so my width is 1/5. So here's what I got going on. I'm going to sketch this curve. I'm going from 0 to 2 over here, and that's my a and b, and I'm using 10 rectangles, so my widths will be right here, the first one 1/5, then 2/5, then 3/5, and so on. So, and I'm going to use left endpoints. So since I'm using left endpoints, my first rectangle will be like this. The second one will go across like this. The third one will go like that. Notice I'm putting the left point here, drawing the width, and coming down and finishing out. Left point on there, drawing it and coming down like that. So that's the key to drawing these. Put the point on the curve on the left side for the rectangle because it said left endpoints. If it was right endpoints, I would do it the other way. The right side of the rectangle would be on there. So now, let's continue on with what we got. The area is the approximations, right, of these rectangles for the delta x times my f of x sub I. Delta x is the width. My f of x sub I is each iteration of the height, right? So right here, they all have the same width. So I can say f of x sub 0 times my delta x. Why did I do sub 0? Because I started at 0. Then I went to the 1/5, right? So I'm starting at my initial spot, f of x, the initial one, plus f of x sub 1. That's why I'm calling, because I'm shifted to the left side, times my delta x, and so on. Right? I'm going to go all the way up to 9 iterations, which, because 0 to 9 gives me 10 rectangles. So basically, here's what I'm saying. I'm going to take out a delta x. They all have this in common. And I'll have f of 0. Then I'll have f of 1/5, f of 2/5, f of 3/5, f of 4/5, f of 5/5, f of 6/5, f of 7/5, f of 8/5, and the last one, f of 9/5. That's how far I'm going out, right? And I can find what each of these is. My delta x is 1/5. Now, f of 0 is 0. F of 1/5 is 1 over 25. How am I getting these? Because I know y equals x squared, right, which is f of x equals x squared. I'm just putting in 0. Then I'm putting in 1/5. Then I'm going to put in 2/5. So this ends up being, the next one's going to be 4/5. 4 25ths plus 9 25ths plus 16 25ths plus 36 25ths plus 49 25ths plus 64 25ths. I think I did it all right. I don't think I missed one. Plus 81 25ths, and then just adding all this up and then multiplying it. I'm going to do it on the side here, and you will get 285 over 125, which is approximately, when you reduce it, 57 over 25 square units. Okay, so that was an example of Riemann sums on an interval from 0 to 2 for y equals x squared with 10 rectangles. So now let's take a look at what we got over here. This is the definition of the definite integral. Now, a while back I told you the integral is going to be this little symbol that looks like this. This was in a few lessons ago when we talked about antiderivative. I said it'll be a symbol that looks like that, right? So the definite integral, if f is a function defined for x between a and b, we divide the interval a to b into n subintervals of equal width delta x equals b minus a over n. So that's everything that we've been doing here. I've got some sort of function on an interval from a to b. I define the number, the delta x, the width, to be b minus a over n, and we let x sub 0 equal a, so that's our first one, then x1, x2, so that's the summation part of it, to be the endpoints of the subintervals, and we let x sub 1 star, x sub 2 star, etc. be any sample points in these subintervals, so that x sub I star is the ith subinterval. So just like we did here, x sub 1, x sub 0, sometimes I may have called it, so x to the I, right? Which iteration I'm doing, the first rectangle, the second rectangle, the third rectangle. That's just saying here, divide it into the widths, and then all these subintervals, which are the rectangles, be any sample points in these subintervals, so that it lies on the ith subinterval, x sub I minus 1, x sub I. Then the definite integral from f from a to b is the following. The integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation of f of x sub I delta x. So from I equals 1 to n, we're going to sum this up. So this is saying that all the rectangles I sum up, the infinite amount of rectangles, is the definite integral. Now, provided that the limit does exist. If the limit does exist, we say then it is integrable on AB. Whoa. Let's back it up. Let's say it again. This whole process, okay, this whole summation process that I was doing is what the definite integral is. So this symbol, this little S symbol like that curly Q, is the definite integral, which is a shortcut to writing the whole summation. So let's take a look. This is the integral sign. Okay, it was chosen by Leibniz, and I'll talk more about Leibniz in the next section. Okay, but just in summary, he was a super famous mathematician along with Newton. So Newton, they say, is the father of calculus, but Leibniz gave us the terminology, the symbols that we use, and how we do it. So it may have, and some say they each independently kind of did it, but Newton is pretty much credited for it, but Leibniz organized it, as that's the best way of saying it. So this integral sign, Leibniz chose it. Why did he choose it? Because look, it looks like an S. It looks like a summation. It's not, this summation symbol was already being used. That was taken. So he wanted to do something a little different. He did this. So it's the limit of the sums. Again, look at how I read this. This is the integral from a to b of f of x dx. Guess what these are going to be? This is going to be your function, right? Dx is going to stand for those widths. So this is going to be your heights times the widths. F of x is called the integrand. A and b are the limits of integration. A would be the lower limit, b would be the upper limit. And then the dx indicates the independent variable is x. So I'm going to take the integral of f of x with respect to x, just like I took derivatives with respect to something. Here the integral is going to be with respect to something because I don't necessarily have to use x, I can use y. So we don't need to use x. I can say the integral from a to b of f of t dt. Notice how this is t, that's got to be dt. This is x, that's got to be dx. You could do whatever you need to do. All right, let's see. Do we have anything else here? No, let's move on to the next page. And let's slide this down. So remember, this is right here, the Riemann sum. The sum from I equals 1 to n of f of x sub I delta x. So that's what we have been doing, is all these Riemann sums. And now we can express it with the integral symbol instead. So the integral allows us to find areas under the curve. So right here, I have my curve. I can use the integral of f of x dx. And then on the integral, I'm going to say it's the integral from a to b. So I will write this out as the integral, this area, the area here, equals the integral from a to b of f of x dx. Now, what happens if you have, we haven't done these, but what happens if you have something go below the axis, such as this one? Notice you have parts of the curve above the axis and parts of the curve below. You're going to get negative areas. And it's okay, because we need a net area. So the sum above the axis will be positive, the sum below the axis will be negative, and it gives you a net area. So it's okay if you have some above, it's okay if you have some below. I know we always say you don't want a negative area, you don't want a negative area. But in these applications, it works, and we're going to take that into account. So when you have a region above the axis and below the axis, you have the integral from a to b of f of x dx equals a sub 1 minus a sub 2. A sub 1 is the area above, and a sub 2 is the area below. So this is a positive area. This is a positive area, but it's below the axis, so we assigned it a negative sign. How about if I said it to you that way? This is above the axis, it's a positive area. This is below the axis, it's still a positive area, but since it's below the axis, we assign it a negative value. Okay, so here's the next theorem. If f is continuous on AB if f is continuous on the closed interval from a to b, this should be if and only if f has a finite number of jump discontinuities and f is integrable on AB, so the definite integral from a to b of f of x dx exists. This was always believed to be true, but Riemann actually proved it to be true. And here's another theorem, and we'll talk about these theorems as we come across them. But here's another one. If f is integrable on AB, then the integral from a to b of f of x dx is equal to the sum of the limits, where delta x is b minus a over n. So this basically means that the sum of all the rectangles is the integral, which is what we just said. So what we did in 5-1, those previous examples, they're all Riemann sums. Now let me talk about one that I haven't given you a specific example of yet, but it's the midpoint rule. All right, in the midpoint rule, it's the integral right here from a to b of f of x dx. It's the sum. Now over here, look at how I say f of x with a bar over it, sub I delta x. So delta x, these are going to be averages. Average of the x right here, the two endpoints, that'll give me the midpoint. The two endpoints of the rectangle, that'll give me the midpoint there. But what I'm going to do is I will find where a, where b should be to do that. So delta x equals b minus a over n, and the average, I'm going to take 1/2 x sub I minus 1 plus x sub I. So it's the midpoint between the two x values. So x bar is the average, which is the midpoint, and this will always yield a better approximation than left or right. So we've discussed left, right, and now midpoints, but can we do even a better approximation? So I've said you have over or underestimate with left, you have an over or underestimate with right endpoints. With midpoints, you can't determine. But do we have to use rectangles? Can we use other shapes? That's the real question. And yes, we can. We can use trapezoids. So let's talk about this one, which is the trapezoid rule. So recall that the area of a trapezoid is 1/2 the height times the sum of the bases. So I have a trapezoid that I drew out for you guys right here. This is the height, these are the bases, and this is our formula for the area. So the area is equal to 1/2 times that height times the sum of the bases. So check this out. If I draw trapezoids, okay, and I'm drawing them like this, where I've got this trapezoid like that. So this trapezoid, I made it, instead of looking this shape, imagine I made it like this, with this piece being a right trapezoid like that, and then I stood it up to where now I have that situation. Okay, so that's what I did there. There's my trapezoid, which would mean this is the height, this is base 1, and that's base 2. So that's what I just did there. Then I could draw another trapezoid and another trapezoid. Now notice this space in between right here. Notice that this would have been, if I drew it as a rectangle, see what it would look like? Whereas if I drew it as a trapezoid, in this case, I'm filling in more of that gap. I'm filling in more of the gap as I draw these trapezoids. So I can find trapezoids and do the same exact situation I did with rectangles, but with trapezoids. But you got to be careful. Your h with a trapezoid will be your delta x, right? Delta x will be the h, and base 1 and base 2 will be, and base 3, right, etc., will be the height this time. This will be your f of x value. Okay, so this is f of x1, or you could say f of x0, in whichever, however you want to say it. You can say this is f of x1, then f of x2, f of x3, f of x4, f of x5. Okay, so what would happen with the formula? Take a look. The integral from a to b of f of x dx using a trapezoid rule would be delta x over 2. Now, why did I do delta x over 2? Because each one of these has an area that's going to be 1/2 delta x, and it's going to be f of xi, right, plus f of xi plus 1, your next iteration, like that. Look at what they all have in common, though. They all have this in common. Each one of these trapezoids will have that in common. So I'm going to take that out. So I've taken it out right here. And I've got my delta x over 2. This was the uniform height over 2. So the 1/2 h. Then I've got my first height, my second height meaning the base, my second base, my third base, my fourth base, and so on. And why did I do 2 right here? Ooh, that's the big question. Why is there a 2 right there? Well, look at what happens. When I'm finding the area of this trapezoid right in here, okay, when I'm finding this trapezoid area, I'm using base 1 plus base 2 divided by 2 times my height. When I'm finding the area of this trapezoid in here, I'm using base 2 plus base 3. Notice I use base 2 again. When I'm finding this one, I'm going to use base 3, and I already used it in the previous one. Then I'll use base 4. When I'm finding this one, I'm going to use base 4 and base 5. So each of these that are in the middle, they get used twice, but the ones on the outsides, they only get used once. So the ones in the middle will get used twice because they're part of 2 different trapezoids, whereas the outside ones will only get used once. So this is a common mistake that you guys forget to put 2's, or you put a 2 on this one also and a 2 on that one. Don't do that. The 2's go just in the middle ones. There's 1 on the end, 1 on the end, and this is delta x over 2. And delta x is the same thing, b minus a over n, and x sub I is a plus I delta x. Notice the 2 being multiplied by the middle terms is what I'm talking about, is because all these heights are being used twice, 1 for each trapezoid. However, the first and last terms are only used once for the trapezoid. I'm going to do an example later towards the end, so we will save that when we do the trapezoid rule ones. There are other methods that we can do. These are called Simpson's rule, one of them. And Simpson's rules, we're doing the same thing, but we're creating parabolic tops. We are not going to cover in the AB course Simpson's rule. Now, approximation methods are good when we have tables of values and we're given equation of the curve, but the exact answer like this is very difficult. We would have to integrate to get the exact answer. We would have to actually take the integral if we wanted to get an exact answer. On the AP test, they will give you tables and ask for approximations, either left, right, midpoint, or trapezoid. And guess what? They won't make delta x uniform. So you'll have to find every single rectangle separately. You'll have to find every single trapezoid separately. All right, at this point, just pause the video, take a deep breath, go, stretch, and then we'll continue. Okay, now let's talk about the properties of the definite integral. First of all, take a look at this one. If I have the integral from b to a of f of x dx, that's like saying negative a to b of f of x dx, and vice versa. So if I wanted to say the integral from a to b of f of x dx, and I switch the bounds, if I flip the bounds and say b to a, then I need to put a negative. So it's equivalent, switching the bounds is equivalent to putting a negative. Here's how I relate it. If you're moving from A to B on an axis, right? You're going in this direction. Well, if you flip it and go the opposite direction from B to A, and you're going the opposite direction, that's where the negative takes into account. So it's the opposite direction, we put a negative. If A equals B and delta x equals 0, so the integral from a to b of f of x dx is equal to the integral from a to a of f of x dx, which is 0. In other words, you haven't moved. Again, I relate it to a number line, right? If you, this is your starting point right here at a. Let me make my number line an actual number line. Okay, so I'm going to go like this, and I'm starting at a right there, and I don't go anywhere. Have I created any area? No, I haven't. So any curve that's about to go up or down has not done anything. It hasn't created any area, so the area would be 0. All right, so now let's look at this first one. The integral from a to b of c dx is c times b minus a, where c is any constant. This will be the height times the width. That's what it's telling me right there. Over these bounds, this is the width. All right, so let's take a look at what we got for number 2 and so on. Okay, so the next one, the integral from a to b, the integral from a to b of f of x plus g of x. So if I'm adding two functions, I can distribute the integral. The integral from, let's go ahead and clear that one out. Okay, the integral from a to b of a constant times a function. That's just like putting the constant out in front. So c times the integral from, so the constant doesn't do anything. We just move it out in front and then take this integral right there. Again, just like up here I had a plus, if I have a minus, I can distribute that negative. So the integral from a to b of f of x minus g of x, just distribute it and do each one separately. Over here, from a to c of f of x dx. Well, what is that? Well, look at this. This plus c to b. From a to c plus c to b is just like going directly from a to b. In other words, if c was in between and I go from a to c, find this area, then from c to b, find this area, it would be just like finding the area from a to b directly. And there's going to be times when you're going to want to break it up. It just makes the problem easier. And that's what this is telling you, is that you can break it up. If f of x is greater than or equal to 0 for x between a and b, then the integral from a to b of f of x dx is also greater than 0. So if the function is greater than 0, the integral will be greater than 0. In other words, if you're above the axis, you're going to get a positive area. If f of x is greater than g of x for x between a and b, then the integral from a to b of f of x dx is greater than the integral from a to b of g of x dx. So if this function's bigger, it's going to generate a larger area than g of x. And then if m is in between, if f of x is in between little m and big M for x between a and b, then m times b minus a is less than the integral from that of the big M times b minus a. This is what this is saying. So here is M, the visual part of it, and here's big M. If I make this rectangle, M times B minus A, M is less than or equal to f of x. So this height is less than the f of x's height, but the big M is bigger than the f of x height. So this rectangle created down here, and the big rectangle created like this, okay, that huge one. Well, f of x will definitely, the area of that will be somewhere in between the area of the little rectangle and the big rectangle, and that's what this is saying. If the function's between those, then the area is going to be between those. So the area under the graph of f is greater than the area of the rectangle and less than the area of the rectangle with height m. All right, here are the visuals for a lot of these. This is the zero width interval, so if I haven't gone anywhere, like that one, the integral from a to a, I haven't gone anywhere, I haven't created any width, and so I won't have any area. From a to b times a constant, well, you can change the height whatever you want, and then that's where that constant ends up. So you're just moving the constant out in front, and it's a multiple of whatever area you get. Over here, it's like adding the two separate areas, finding this integral and the other integral to get the big one. So that's what they're saying. Just find each area separately and then add them together. So the integral is distributable because you can find independent areas. Over here, the additive, if you're going from A to B, then B to C, it's the same thing as going from A to C directly. So it's this area plus this area. These are all the ones that we just talked about, but the visuals for them. The max minimum inequality, so this is the one where if the minimum is F times B minus A, and here's the one in between, and that's like this one that we just talked about where it's in between. Okay, and you could do it the other way around, where it's greater than, the f of x is greater than, so a to b of f of x dx will also be greater than g of x, and that's the one up there that we talked about, where you have one function bigger than the other, so it's going to create a bigger area. All right, so now let's do some examples. So the rest of this lesson, we are just going to do a bunch of examples. So for number one, it says, if f of x equals x squared minus 2x, and x is between 0 and 3, evaluate the Riemann sum with n equals 6, taking sample points to be right endpoints. So we're going to do right endpoints, and I've got my function, x squared minus 2x. So let me graph this function real quick, and graphing this will give me this situation, and I'm going from 0 to 3. So when I put in 0, I will get 0. When I put in 1, I will get negative 1. And then when I put in 2, I will get 4 minus 4, which is 0 again. And then when I put in 3, I will get 9 minus 6, which comes out to be 1, 2, 3 up here. So I've got this function, this parabola that looks like that. And I want to find Riemann sums, n equals 6, taking the sample points to be right endpoints. So right endpoint means I'm going to start at delta x equals b minus a over n, and my a and b is this. And we're going to say that this is going to go from 3 minus 0 to over 6 rectangles. So each one will be spaced by a half. So right here is going to be the right endpoint for my first rectangle at 1/2. My second rectangle will have this right endpoint and will look like this. My third rectangle will have that right endpoint and look like that. My fourth rectangle will have this right endpoint and be flat. Then my fifth rectangle will have this right endpoint and look like this. And then my last one will have this right endpoint and look like that. So those are my 6 rectangles. 1, 2, 3. The flat one is 4, 5, and 6. Now, writing this in an integral fashion, this is the integral from 0 to 3 of f of x dx, which is the integral from 0 to 3 of x squared minus 2x dx. That's if I wanted to write this in integral form. So now let's find the area. The area is going to be the sum of the delta x times my f of x sub I. This is the width, times my height. And in this case, each width will be uniform and it'll be 1/2. So I've taken my delta x out of each one. Now, since I started with right endpoints, my first right here will be at f of 1/2. My second right here will be at f of 1, and so on. So this first rectangle will be at f of 1/2. The second rectangle will be at f of 1. The third will be at f of 1.5. Then f of 2. Then f of 2.5. And my sixth rectangle will be at f of 3. So 1, 2, 3, 4, 5, 6 rectangles. Okay, so my sixth rectangle was at this last spot, f of 3. My first rectangle was shifted over by 1/2. So let's find this. This ends up being, well, f of 1/2 comes out to be -3/4. F of 1 comes out to be -1. F of 1.5 comes out to be -3/4. And then 0, because this has 0 height, right? Plus f of 2.5 comes out to be 1 1/4, and f of 3 comes out to be 3. Finishing all this up, I get 7/8 square units as the total area. Now remember, some of this area was negative because it was below the axes, and some of the area was positive above the axes. So these rectangles that were above the axes. Now, I'm not going to say the area, I shouldn't really say the area is positive and the area is negative. I should say the areas, but since it's below the axes, we assigned it a negative value. All right, let's move on to the next example. Over here, let's take a look at what we got. Let's enlarge this. And it says, use the midpoint rule with n equals 4 to estimate the integral from 1 to 5 of x cubed dx. So let's quickly graph this out again. And I've got my x cubed graph, but this time I'm starting at 1 and going out to 5. And remember, x cubed comes up like this and through here, and it'll come up at 1, 1 right there, but then it drastically moves up like that. But now I'm using midpoints, so these values are all going to be midpoints, and I know n is 4, and I'm going from a to b right there. So my delta x is going to be b minus a over n. So b is going to be 5 minus 1 over 4, which gives me 1. So that means I need the midpoints between 1. So each one of these is going to go from 1, 2, 3, 4, 5. But I need the midpoint between, this is my first one, f of 1, and that's f of 2. So I need the midpoint in between that, so that's going to be at f of 1.5 will be my first one. Do you see how I got that? And my delta times my delta x. Then f of, well, what's between 2 and 3? That midpoint is going to be 2.5 times my delta x, and so on. So let's do all this. So the integral from a to b of f of x dx is going to be the sum from I equals 1 to n of f of x sub I, the average delta x, and we said this is approximately my delta x's I'm going to take out, which is 1 times, now this will be f of 1.5, f of 2.5. Now between 2 and 3, we said 2.5. Between 3 and 4, this will be f of 3.5. And between 4 and 5 right here, there is my midpointed rectangle. That will be f of 4.5. Finding all these values, I will get 3.375 plus, I already did this on my calculator ahead of time just to speed things up, 6.25 plus, this will be 42.875. The last one will be 91.125. Okay, adding all these up, I get an approximate area of 153 square units. Okay. Okay, take a look at the next one. It says express the limit as a definite integral on the given interval. So we need to take a look at this. Here's a limit. This is a summation. So that's an area. So that means I need an integral. And now look at, here is my a and my b. So that's going to be from pi to 2 pi. Now I need to get an f of x and a dx. So let's see if we can clean this up. It goes from pi to 2 pi. Now let's see if we can find what an f of x and is going to be. Well, this is my f of x right there. This will be the cosine x over x, and this is your dx, my delta x. There you go. There it is, expressed as an integral. And then the next one, it says, use the form of the definition of the integral given the theorem 4 from your text. So we'll take a look at that on the integral. So basically, we need to find the exact value of this problem. So let's take a look at what we have to do. So now I'm taking a look at my bounds. My bounds are from 1 to 4. So a is 1, b is 4. Delta x is going to be 4 minus 1 over n, because I am finding an exact integral. I am finding an exact area here. Then that's what this theorem had me do. So 3 over n. So then x sub I, in this case, is a plus I delta x, is what I'm going to call it, because I'm choosing to use right endpoints here. So my x sub I will be equal to a is 1 plus my I, in this case, is going to be 1, or my I, times delta x. So I'll have 3I over n in this particular situation. This will be x sub I. And my a is 1, and this will be 3I over n for my delta x. So it's I times delta x. All right, so now let's see. We have the limit as n goes to infinity, and this is going to be the sum from I equals 1. I'm starting at 1 to n, and this will be f of x sub I delta x. So that's going to be the limit as n goes to infinity of this summation, I equals 1 to n. And now let's put in our f of x sub I. So your first iteration here will be 1 plus 3i over n squared, right? Plus 2 times, well, that x this time is going to be 1 plus 3i over n minus the 5, right? Times now all these 3 over n, my delta x. So there's my equation, and there's my delta x. So this will give me the limit as n goes to infinity of, I'm going to take that 3 over n out right here, and I'll say that this is the sum from I equals 1 to n of this. I'm going to work this out. This is going to end up being 9i squared over n squared plus 12i over n minus 2. So what I did is, all I did was work this problem out over here. Okay, FOILed it out and combined the like terms. And this ends up equaling, now look at what's happening here. It's going to be the limit as n goes to infinity. Now, I'm going to take 27 over n cubed out. That's what I'm choosing to factor out of this. And it'll leave me with the sum from I equals 1 to n, and this will leave me with I squared plus 36 over, notice that I'm going to do each one of these separately. I did this one, now I'm going to do this one, and then I'm going to do this one. Okay, but that's why I took out n cubed, because that would be the common denominator between these three terms. So that's what I did there. I took out a common denominator. Okay, so that would be, we said I squared here. It doesn't look like it, but that's I squared. And this is 36 over n squared. And this will be the sum from I equals 1 to n. And when I take that out, I'm left with an I. Minus 6 over n. And this will be the sum from I equals 1 to n. And when I take out what I had with the common denominator, it would just be 1. And these now equal the limit as n goes to infinity of 27 over n cubed. And now I'm going to replace each of these with a formula. So this will be n times n plus 1 times 2n plus 1 over 6 plus 36 over n squared plus, or times, sorry, times the formula for I, which is n plus 1 all over 2, minus 6 over n, and the formula for I of 1 to n is just n, like that. Cleaning this up, I get the limit as n goes to infinity, and this is going to give me 9 over 2 times n plus 1, 2n plus 1 squared over n squared, and these will reduce out when I go to infinity, right? Plus, I'm just kind of showing you a little bit there, 18, and this will be n plus 1 over n minus 6. And when I clean all this up as I go to infinity, these will go away. I'll be left with this 18 over 2. That's what I end up, the n squareds will go away, but I still have this 2 times the 9, 18 over 2. Plus, well, these will reduce out when I go to infinity. It goes, right? Those reduce out when I go to infinity. So I'm just left with this 18 minus the 6, and that gives me 21 square units. That was a tough problem. That was a very tough problem. Next, it says evaluate by interpreting in terms of areas. All right, let's see what we can do here. We have this is the integral from -1 to 3 of 3 minus 2x. So our function is 3 minus 2x. Let me graph that for you guys real quick. And we end up with this situation when I put in 0, right? Oh, well, let's just start with -1. When I put in -1, I'm going to end up over here at 1, 2, 3, 4, 5, right? -1, I'll end up at 5. 1, 2, 3, 4, 5. When I put in 0, I'll end up at 1, 2, 3. When I put in 1, I'll end up at 1. When I put in 2, I'll end up at -1. And when I put in 3, I'll end up at -3. So I have this linear model, this linear graph, and I'm going to find the areas of this and interpret it. Okay, well, here's what I'm going to do, basically. I'm going to find this rectangle right here, and then I'm going to find this rectangle right here, and just add those together. That's all I'm going to do for this problem. So this crosses right here at 1.5, right? You can find that out by saying this equals 0. So 3 equals 2x, x equals 3 halves. That's my x-intercept, so that's where it's going to cross. So I'm going to take the integral from -1 to 3 halves plus the integral from 3 halves to 3. Okay, that's what I wanted to do there. So for this triangle, 1/2 times the base, which is, this will be 2.5, so 5 over 2, and times its height right here will be 5, plus this integral, well, this triangle, that's going to be 1/2, and it's going to be 1.5 in length, so that's 3 over 2, and the height here, but be careful, we're going negative, that's going to be -3. cleaning all this up, I get 25/4 plus negative 9/4 for a total area of 16/4, which is 4 square units. All right. Next, we got 2 more left. We're going to do a trapezoid rule one, and then we are going to do another one where we find an exact value and compare. So for this trapezoid rule one, it says find the area under f of x equals 1 over x from 1 to 2 using trapezoid rule with n equals 5. Okay, so taking a look at this one, if you take a look at the graph real quick, you have 1 over x. So if I were to sketch this graph from 1 to 2, here's 1. When I put in 1, I get 1. When I put in 2, I will get 1/2. So it's this under this particular part of the curve is what I'm looking for, that area under there. Okay, so for trapezoid rule, this will be the integral from 1 to 2 of 1 over x dx if I wrote this as the definite integral. So delta x is going to be a to b, so 2 minus 1 over 5. So these are going to be spaced out by 1/5. So that tells me I'm going to start at f of 1, and then I'm going to go to f of, I'll put a comma, f of 1 and 1/5, comma, the next one will be f of 1 and 2/5, comma, f of 1 and 3/5, and so on, and I will end up with my last value at f of 2, right? But now, because I'm using the trapezoid rule, I need to put a 2 in between all of these except for the first and the last. Oops, I'll say this is the last right here. So this does not have a 2, that'll have a 1. All these other ones have 2 in between. And why do they have a 2 in between? Because I'm using that particular base in 2 different trapezoids. All right? So t sub 5, trapezoid with 5 subintervals, is going to be 1/2. Remember, trapezoid is 1/2 times my delta x. And in this case, this will be my height. And then my f of x, we'll say base 1 plus base 2 for now. Okay, and those are my f of x's. So we'll just keep it like that. Now, my delta x is constant, so I have 1/2 times 1/5. This is my delta x. Now, this will be f of 1 plus 2 times f of 1 and 1/5. Now I'm going to write it all out. Plus 2 times f of 1 and 2/5. Plus 2 times f of 1 and 3/5. Plus 2 times f of 1 and 4/5. Plus, now this will be 2 times f of 5/5, which is just f of 1 and 5/5, right? That's 2. So plus, it'll be 1 times it. I'm sorry if I said 2. 1 times f of 2, okay? So I made it all the way over. Now remember, 1's on the end and 2's in between. Because those get used twice, the end pieces only get used once. So you have all your trapezoids in here that will get used twice, all of these, whereas the end piece right here and right here only get used once. Okay, so cleaning this up, I'll get 1/10, and then I will tell you what these values come out to be just to make this a little bit easier. This first one is 1 plus 2 over 1.2 plus 2 over 1.4 plus 2 over 1.6 plus 2 over 1.8, and the last one will be 1/2. And you get a final approximation of 0.695635 square units. Whew. All right. And our final problem over here for this lesson. This is a very long lesson, so we are down to it. Okay, find the area under the curve of f of x equals x squared from 1 to 2 using a trapezoid rule when n equals 4 and compare it to the exact value. Well, I'm going to save you some hassle from doing the infinite number of rectangles or infinite number of trapezoids because we're going to learn an easier way here pretty soon. And I'm going to tell you that the exact value on this particular problem, the exact value is 7/3. Okay? Square units. So now let's do the trapezoid rule again. T sub 4. We have 4 subintervals, so delta x is going to be 2 minus 1 over 4. So this will be 1/4, right? Each of these will be 1/4. So I need 1/2 times my delta x times my base 1 plus base 2, these summations. So this will be 1/2 times 1/4. Okay, let's do the summations of each of these bases. So I'm going to start off with my trapezoid rule at f of 1. And then I'm going to move 1/4. So 2 times f of 1 and 1/4 plus 2 times f of 1 and 2/4 plus 2 times f of 1 and 3/4 plus f of 2. Again, 2's in the middle ones, 1's on the end. So this is going to be 1/8 times, and I will tell you what these are. This is going to be 1 plus, this will be 2 times 25/16 plus 2 times 36/16 plus 2 times 49/16, and the last one will just be 4. Adding all this up, you get 75 over 32, which is equal to 2.34375 square units. All right. Now, I want you to think of something, and we'll talk about this further in detail in class. But if you take the left endpoint and the right endpoint approximation and add those up and divide by 2, do you think you get the midpoint rule? And I already talked about this in class. No, you don't. I also talked about it earlier in the lesson. No, you don't. Guess what you get when you add the left and the right? You get the trapezoid rule. So when you add the left ones and the right ones and take the average of those two, you will get the trapezoid rule. So I will show you why that happens in class, but it's a pretty elaborate proof. All right, so thanks for watching. Hit that like and subscribe button, and I will see you guys in the next video.